Alright, last part of Unit 3 and the last lesson of how fields are used to move electricity, or electrical energy, I should be more specific there. Alright, so mentioned earlier about, in a previous lesson about the benefits of AC is that you can get low power loss and you can change the voltage. So as we'll find here, what we actually do to get the low power losses, we change exactly that, change the voltage. So what do we do that? We use a thing called a transformer. So transformers are things that transform the voltage from one to another. So here's a very simple example, or simple diagram that shows that. Now there's some videos on transformers. Right, here's the diagram. Right, very simplified diagram. They don't actually look like this, but simplified diagram. Basically, in a transformer, what you have two coils of wire. They use some iron in the middle here to link and channel the fields. So what do? Over this end on your input here, wrong colour, on your input over here, you have a certain number of turns in your coil, and you have a voltage here in your coil, and we're calling this the primary coil with the input. And so this voltage is varying, so if this voltage varies, then the current through the coil varies, and that produces a changing magnetic field, and that changing magnetic field gets channeled around here. Now this is kind of simplified and it's expanded, but in reality the two coils is just one piece of wire, and the two coils are wrapped in together. But anyway, with this simplified, we've stretched it out. So because then you get you've got another coil over on the right, which is our output, which is our secondary coil. So we have a certain number of turns there in our secondary coil. And so again, we've got our magnetic field, which is changing, and a changing magnetic field produces and induces a current and a voltage in our secondary. Alright, so alternating current, you get a field produced in the primary coil which induces a current, voltage / EMF in the secondary coil. Alright, so it turns out that there's a good relationship between, and this is missing in your notes in the red, so the voltage across the primary over the voltage across the secondary is directly related to the number of turns in the primary and the number of turns in the secondary coil. Alright, so if we want to change our voltage, we can look at the numbers of turns, or the turns ratios it's sometimes called, and then we can figure it out, because the voltage if we do a bit of rearranging of this, you find that the voltage in the secondary would be the number of turns in the secondary over the number of turns in the primary times the voltage in the primary. Alright, so we can, by adjusting this bit, we can change whether we want the voltage in the secondary to be bigger or smaller than the voltage in the primary. Alright, now ideally power will be transferred. Now reality is that it's not, because you get some heat happening, but for our purposes we're using ideal transformers. Power in is power out, so that means the voltage in the primary times the voltage, the current in the primary would be the voltage in the secondary times the current in the secondary. And so if we rearrange that so that we get voltage of the primary over the voltage of the secondary, then that's the current in the secondary over the current in the primary. Alright, and of course if we want to add this to it, then that's the number of turns in the primary over the number of turns in the secondary. So we can then change things as we wish. So here's an example. Alright, so here's something that's, fairly typical. Transformer supplies a model train that operates on 12 volts from the mains of 240. If the number of turns in the secondary is 100, what's the number of turns got to be in the primary coil? Alright, so we've got voltage and numbers of turns. So the voltage in the primary over the voltage in the secondary is the number of turns in the primary over the number of turns in the secondary. And our primary is our 240 volts. So that's what we're plugging into. So we'll do 240 over, we want 12 volts out. The number of turns in the secondary is 100. What's our number of turns in our primary got to be? So if we then figure out what that's got to be, now I've done it a different way in the notes, but it doesn't matter. Timesing both sides by 100. 100 times 240 divided by 12. Then you get your number of turns is got to be 2,000 turns in the primary coil, so that we get 12 volts out. Alright, in part B it says if the crane requires a current of up to 4 amps, what will be the current and power drawn from the mains? Alright, so what do we got? This is our secondary current, and we got our primary current, and then our power is also from the primary as well. Alright, so let's have a look and see what we can do here. So back to this. Alright, so now we could use these two if we wished. Voltage in the primary, voltage in the secondary, current in secondary, current in the primary. So let's go with that. So VP, VS, IS, IP. Alright, so voltage in the primary 240, 12, just check that. Current of up to 4 amps in the secondary, okay, so 4 over the current in the primary. Do a bit of rearranging, times both sides, flip both sides. Times by 4. And when we do that, we get 0.2 amps current in the primary. Okay, so next. Part of that question, the power drawn. Yep. So the power drawn from the mains, so we're talking mains, power, and so power P equals VI, and we're talking the mains, so the mains is 240, and we just found out the primary current was 0.2, and so that's 48 watts. Alright. Alright, so power transmission. So that's a simple example of the way things work. So if you model train people, slot cars, all sorts of stuff work on that principle. So for us though, we need the power, we need to get it to our homes, so power transmission. And we want to get it there without losing too much. Because even though the wires, most of the wires that we use have low resistance, there is resistance in the wires. And it turns out that power loss, you know, power transmission, power loss, the main thing that we can look at with power loss is the things that I squared and R. Now there's a few different versions and this is one of them, but this is the one that's most useful. I squared R, because we can work out the current flowing through a wire fairly easily. You know, you've got meters these days that can do that quite directly without even connecting into the actual circuit. They put a ring around the circuit and do it that way. I won't go into how they do it, but it's based on the stuff that we've just been talking about. And then the resistance, well, you can work out the resistance per metre of a wire, and then if you got so those two things are easy to work out, whereas the voltage for power loss would be the voltage drop across that wire, more difficult to work out. So power loss, I squared R. So resistance, get that as low as possible. All right, so we can do that by having, because remember, one of the things is it's the length and over the area. That's what the resistance is proportional to. Now the length, can't do much about that, because if you've got to get power from the power station to Melbourne, it's got to be a certain length. So we can make these wires big, but then you've got a limit. You know, once they get too big, they get too heavy, and they get so. Reducing R, while we can do it, there's a limit to what we can do. So what can we do here? Well, if we reduce the current, and so what we can do is we can reduce current, because as we've just looked at with our transformer, and here's the one that we've got here, there's current involved there. So we can reduce current, and if we want the current to go down, what we've got to do is we make the voltage go up. So we put voltage and high to transmit, so that gives the current low power losses. And so here's an example. So I've worked out this table here. So we've got a power station, 400 megawatts is what it produces, and we want to transmit it along the power line, and for this example we've got 4 ohm resistance. Alright, so when we look at it, and I probably kind of put this in the wrong order really, so if we look at it, if you use 66 kilovolts, so 66,000 volts is the transmission voltage, you get quite a high current, you get a big power loss, 150 megawatts. So you're actually losing 37% of your power in the wires because of this high current. So if you instead change that voltage and did it at 220,000 volts, your current's dropped quite a bit. Your power losses dropped a bit, but you're still losing 3.3% of your power in the wires. If we then go to 500 kilovolts, so 500,000 volts, more significant drop in the current, drop in the amount of power loss, and then again now only 0.6%. If we then double that and go to 1,000 kilovolts, current drops by half, the power loss drops, and the percentage is at 0.2. All right, so again, so this is where we want to be distributing our power across at those high voltages. So from the power stations into Melbourne or wherever it's going, they're high voltage, relatively low current, and so their power losses are lower, because we don't want power being used to heat up the transmission lines. We want it to be used to be turned on our lights. Alright, so let's have a look at an example. Okay, so we've got a 240 volt AC power supply of negligible resistance connected by wires of total resistance 4 ohms to a motor. So here's our 240, get there, and here's our motor. Alright, then our motor has a resistance of 116 ohms, and our wires have a resistance total of 4. Okay, the current flowing through the wires. The current going through the wires, so if I'm looking for A, V equals IR, the voltage is 240, the current flowing through the wires times the total resistance, which is 4 plus 116, so 240 equals 120I, so the current flowing through the wires is 2 amps. Alright, the power loss in the wires. Now remember, power loss, when we're talking here, power loss, while there's 3 ways, P equals VI, V squared on R and I squared R, when we're looking at power loss, I squared R. Always use I squared R for power loss. Alright, so for B, the power loss equals I squared R. Current we just found out to be 2. 2 squared times the resistance, which is power loss in the wires. Ooh, nearly wrote 120 there. Power loss in the wires, it's 4 ohms. And so 16 watts. Alright, so 16 watts of power loss. The voltage drop across the wires. Alright, so the voltage drop across the wires, V equals IR, if we use that. So the current in the wires is 2. The resistance of the wires is 4. So there's, whoops, not 80, 8 volts drop in power. Alright, D, voltage or potential difference across the motor. Alright, so if we've got a total of, whoops, wrong one, going the wrong way here. Let's rub that out, shall we? There we go. That's better. Alright, so if we've got a total voltage of, again, 240, and we've got 8 volts gets used up in the wires. That's what we just got here, up in there. 8 volts used in the wires. So we've got 232 volts left for the motor. So the motor is operating on 232. Alright, power converted in the motor. We can use any number of, so for D, P equals VI will do the job nicely. I've done different in the notes, but it doesn't matter. The voltage is 232 for the motor, and the current that was running through was 2. Yes, just remind myself of that. and so for 64 watts gets used. Alright, so there's a couple of little things there. We talked about transforming high voltage because that's what we transmit at so that we get low power loss. So what does our power distribution, what does it look like? So this is power distribution. Alright, so there's a couple of videos that you can look at there about the electrical grid, and then there's a couple of nice, interesting ones, spacer installation on a very high voltage power line there that from a helicopter. That's pretty cool. See what they do so they don't get zapped. And then a wind turbine tour. They're more interest than anything. Excuse me. Alright, so there's a bit more information in your notes about certain voltages, but let's have a look at the diagram. So this is kind of what our transmission thing looks like. So we go to our power station, we produce our electricity, it goes into a transformer, high voltage, boom, high voltage, and then that gets transmitted down here. Hydro power station's a little bit different. Alright, so then that gets to some terminal station, so that's a big thing, right on the outskirts of the city. That changes a little bit to the voltage is down low, it doesn't need to be as high. Then it goes to, its suburb, there's a bigger one in the suburb. And then that steps the voltage down a bit lower. And then you get to, sometimes they're on the ground level, sometimes they're not. The transformer are out. So this one here is for trams and trains, so that doesn't affect us in our homes. Alright, and so then it keeps going, and then we get one that for underground power on the ground or on the street pole, which then goes down to our 240s and then into our house. Alright, so that's effectively kind of how it all happens, that we're getting our power from. Alright, and so this one here is, as it says, the Malvern Terminal Station, so this is the big suburb one. Alright, incoming voltage, so it's coming in at 220,000 volts. And our outgoing voltage, see, it's going out at 66,000, so that's... Alright, so then that heads off and off it goes and gets changed again a bit more. Alright, now sometimes things need to be generated, so sometimes like films, for example. Here's an example that uses... Alright, so here's some examples, like, as I said, films. We need lights on the film set, and we need to generate, because they could be, in the middle of nowhere. So we need to generate electricity to use those lights. Alright, now you can't put the generator too close to the set because, you're going to get the sound of that. So they've got to be a bit away. So in this example, we've got a generator down here that generates 400 volts, 20 kilowatts. We've got some transmission lines at 500 metres long, total resistance of 5 ohms, and then we've got our lighting. So first question asks, what's the current in the cables? So the current in the cables, so if we just use P equals VI, I'll go to the next one. So for part A, if we're using P equals VI, so our power is 20 kilowatts, our voltage is 400, so 20 kilowatts, 20,000 watts. Voltage was 400. What's the current? And so when you do that, that's 50 amps, which is reasonably high. So part B says, what's the voltage drop across the transmission cables? So V equals IR, Ohm's law helps us with the voltage drop. So the current through those cables is 50, and we're told, I think, we're at 5 ohms. Yep, 5 ohms is our resistance. So our voltage drop is 250 volts. It's a big voltage drop, seeing as it was only 400 is produced. So what is the power loss in the cables as a percentage of the power supplied by the generator? So see the power loss in the cables. We can use that calculate that in a couple of different ways, but let's use because we've got some. So C, power loss, as I've always said, is I squared R for power loss. So the current was 50, not 50 degrees, 50 times the resistance, which is 5, and when you do that, you get 12,500 watts. Now it asks us to do that as a percentage. So that's 12,500 over the produced amount, 20 kilowatts, so 20,000 times 100, and at 62.5% of the power produced is lost. So that's a lot of cost in diesel for not much return. All right, the last part of that says, what is the voltage supplied to the lighting? Well, when we look at our 400 volts being produced here, so then our voltage drop across here, then whatever's left is the lighting. So our voltage drop across those wires is 250. So the voltage that we've got left for our lighting is our 400 minus the 250, which is 150 volts. So at 150 volts left for the lighting, that lighting's probably not going to be working too well, given that they're 400 volt lights, if there's only 150. So what can we do about that? Well, what we can do is this. All right, as it says there in your notes, that distance the voltage drops is too much to leave sufficient voltage to operate the lights at their designated voltage. Given the noise it generates cannot be moved closer, therefore step up and step down transformers with turns ratios of 20 are used. All right, so what we've got here is the turns ratio. So here in our generator, we got 1 in our primary, 20 in our secondary, and then when we come down the other end, we reverse it to step the voltage back down. All right, so the questions that we're asked about this setup is, what is the current in the cables? Whoops, gone the wrong way. So the current in the cables, so we've got some current that's going to go here. What is it? So what we need to do is we need to look at this particular transformer at the start there, and we need to have a look at what it produces. Alright, so let's have a look. So for A, current in the cables, we'll worry about that in a minute, but what we know is that the voltage in the primary over the voltage in the secondary is the number of turns in the primary over the number of turns in the secondary, and the voltage in the primary is 400 over the voltage in the secondary, 1 in the primary, 20 in the secondary. Do a bit of rearranging and we find that the voltage in the secondary coil is 400 times 20, which is 8,000 volts. Don't put your hand on it. Alright, now we're asked about the current in the cables. So if we look at and we treat this as an ideal transformer, then our power in the primary and our power in the secondary would be the same. So in the primary we've got 400 times sorry, I don't need that, do I? Because in the primary, we're told that our power in the primary is 20,000, haven't we? See, 20 kilowatts, so 20,000 in the primary. Power in the secondary, though, is the voltage in the secondary, which is 8,000 times the current in the secondary. So when we work that out, you find that your current in the secondary is 2.5 amps, much lower. Alright, so B, what is the voltage drop across the cables? So when we're looking at that, V equals IR. We've now got, and so in the cables is the secondary, current in the secondary. And the resistance of our cables, we're told there it is there, 5 ohms. So the current in the secondary was 2.5 times your 5 ohms, which is then 12.5 volts, much better than the 250 volts before. Alright, so I've actually labelled that incorrectly, haven't I? This is B, not C. Alright, C, power loss in the cables is a percentage. Alright, so our power loss is I squared R. Again, the current in the cables, 2.5 squared, times the resistance of the cables, which is 5. So our power loss this time is 31.25 watts, much better than before. And so our percentage power loss, 31.25 over 20,000 times 100. And when you work that out, you get 0.16%. So there's not much in comparison, a lot less. Alright, so the last part of the question says, what is the voltage supplied to the lighting? So what we now need to do is we now need to look here. Alright, and we want to know this voltage here. Now remember, what we had produced here, there's 400 volts there, 400 volts there, and then it steps it up to 8,000. So there's 8,000 there. Because there's some resistance, there's a little bit of voltage that's lost, and that is this much here, or voltage used in the cables, 12.5. So 8,000 minus 12.5. So 8,000 minus 12.5. Let's go 7,988 volts. As good as. So that means that here we got 788. We want to know the voltage there. We've got our turns ratio. Remember now that's 20 in the primary of this and 1 in the secondary. So let's go with what we need to do. So voltage in the primary over voltage in the secondary is number of turns in the primary over the number of turns in the secondary. So now the primary coil has got this coming into it, 7988. Voltage in the secondary is what we're after. The primary coil is now the one with 20 over 1. You've got to rearrange, so the voltage in the secondary will be 7988 divided by 20, and you work that out, and that comes out to 400 volts when you round it up. Alright, so much nicer. Alright, that's it. Make sure if there's anything that I've been vague with and procrastinated on and you're not sure about, make sure you ask. There's those few videos and there's some text questions. And that's it. That's the last bit for Unit 3.